I'll start with quite an open-ended question. Do you think it will eventually be possible for fully dexterous robotic AI to emerge from an algorithm as simple as reinforcement learning?
So I think that when we look at reinforcement learning applied to real world robotics, there are a lot of factors that often people overlook when they train simulation only agents, which is where a lot of the foundations of deep reinforcement learning are coming from these days. So a couple of these are fundamental differences. One being that reward functions don't kind of magically appear for free, and actually we have to tell the robots what those reward functions are in the real world. That there's not a sort of underlying mathematical formulation for a reward function that the robot just happens to know about. And so if we did want to train a robot to be able to perform any task in the world, then somehow we would have to define all the reward functions for all of the tasks. And often that's done with providing a demonstration of the task. And then that essentially becomes imitation learning rather than reinforcement learning, or at least a combination of the two. So defining the task using imitation learning, and then perhaps solving the task using reinforcement learning. So so one thing is that it's actually not so simple as saying let's just use reinforcement learning for everything, because there's got to be some kind of way of defining those tasks in the real world. But also I think that it might be possible for a human to go away and define reward functions for every conceivable task, and scaling that up using data collection from lots of humans with lots of demonstrations might be possible. But then chaining together those skills, so how a robot would decide on which skill or task to perform next, that's something that reinforcement learning isn't really going to solve. Because you would then essentially have to have an extremely pure reward function, like I don't know, survive, or always do what the human says, or something, which is too pure, I think, for a robot to learn through something like reinforcement learning, because that's essentially how evolution happened. And I don't think we're going to be able to replicate evolution in the real world with robots or even with simulations.
Do you think then that's a fundamental constraint? Because that's actually just what I was going to quickly say, and then I'll pass over to Ronnie as well. But what I was going to say is, maybe right now, obviously, when we have very specified subgoals and everything, then that makes a lot of sense. But just hypothetically, when we talk in the abstract of where the future could take us in, centuries, given that evolution has demonstrated that a simple evolutionary algorithm seemingly has generated very sophisticated intelligence. Do you think that's something that's within the realm of possible, even if it's a little bit, far-fetched today?
I think philosophically it's possible, but I don't think technologically it is, because it would result in too much failure, and it would just be so expensive to have so much failure in terms of both the hardware, different hardware setups evolving. If we're talking about just applying evolutionary algorithms to physical robots, then I think the issue is what do we define that pure reward function to be? Because we can't do survival anymore. That's a robot is going to survive just by keeping it plugged in. Also, it then raises these kind of sci-fi questions of, well, if a robot's only goal is to survive, then what on earth is that going to lead to? So defining that pure reward function of an evolutionary algorithm is very, very difficult. And often people use evolutionary algorithms to enable a robot to solve specific tasks by exploring the world in a very, very diverse manner. But that's still constraining the robot to just learning specific tasks, which then will need to be defined by humans. So I don't really imagine that we will solve this through at least the first generation of kind of AI that appears to be human level, coming from pure evolutionary
Sure,
approaches.
sure. So do you have any thoughts to weigh in on this, Ronnie, you think?
Yes, I think like there's 2 points that I kind of want to discuss related to that, because so the first is the nature of like the simulated environments in which like the reinforcement learning or imitation learning is usually done. So the current reinforcement learning approaches, you kind of have to train in simulated environments, because there isn't a way to like have that amount of like exploration or sort of run the number of trials needed to actually do it in the real world. So I was just wondering, like, Ed, do you think there is a limitation, kind of like a severe limitation introduced by using these simulated environments? Because obviously the physics or the accuracy of the simulations aren't anywhere, near what the real world actually does. So there's kind of like all these quirks or like, kind of like anomalies that are introduced in the simulations that don't exist in the real world. And there's lots of stuff in the real world that isn't really modeled in the simulations. And so I was just wondering, like, what are your thoughts on that? Do you think like simulations are the way we should be training these agents, or do we need to like go to the real world?
Yeah, I think simulation-based robot learning is problematic, and I don't think this is how we should really be training robots. I think it's fine to be developing core algorithms, but I think we shouldn't imagine that robots are going to emerge with human level AI or dexterous capabilities just through simulations. And there's a couple of levels at which simulations differ to the real world. So the first level is simply not being able to model real world dynamics. So some people will say, oh, okay, well, we'll just train robots in simulation and then we'll just deploy them in the real world. And that does work for some specific cases where we can kind of overfit the simulation parameters to a specific task, and we can do quite a lot of engineering. So something like locomotion for quadrupeds has emerged as being something where we can actually do quite good sim to real transfer. But that's a very well-defined task with quite a pure reward function, which just says, well, keep moving forwards as much as you can. Whereas for manipulation, there's billions of different tasks out there. So you couldn't really overfit your parameters to all of these different tasks. And then the other level where there's difference between simulation and reality is just the setup of how training actually works. So in simulation, you have this reward function for free, and also you have automatic environment resetting. In the real world, you don't have either of those. The reward function has to come from a human defining the reward function, let's say, for a new task, and the human would have to reset the environment every time the robot fails. So when you have that kind of difference between simulation and reality, the actual algorithms themselves are developed within a different paradigm as to how they would actually be trained in the real world. And therefore, reinforcement learning researchers are optimizing those algorithms towards different setups than they would actually be deployed in the real world. And as such, the researchers probably aren't optimizing them in the right way under the setup that they would actually be deployed in the real world. So one example of that is a lot of reinforcement learning algorithms optimize purely for data efficiency. So you have these graphs of where the y-axis is success rate and the x-axis is the amount of data. And that's quite a pure machine learning metric, and it makes a lot of sense in the machine learning community. But when you take that into the real world, what we really care about is time efficiency, or maybe the amount of time that a human spends teaching a robot. And that has to then factor in things like the setup of the reinforcement learning algorithm in the real world. What extra apparatus do you need? How much time the human would spend providing demonstrations or resetting the scene. And when you start to factor in all of these, then actually the pure kind of reinforcement learning approach doesn't look so appealing anymore, because there are a lot of human has to do there, which are a burden on us beyond simply the amount of time or the amount of data that the robot will be collecting.
Yeah, I think that makes a lot of sense.
So like roughly, how efficient would you say current reinforcement learning algorithms are compared to kind of actual biological learning? Like in terms of the number of episodes or the number of kind of trials that these agents need to do before they can actually learn a skill?
Well, I think if you're talking about biological learning in terms of evolution, then probably much quicker. To get to human level capabilities, it took billions of years, whereas robots can learn much quicker than that. But if you're talking about in terms of comparing to how quickly humans learn, then certainly much slower. And really, the only things that humans use reinforcement learning for are kind of skills where you have to become an expert relative to other humans. So playing sports, for example, or playing musical instruments where there's some kind of muscle memory or precise kind of dexterous manipulation required. Whereas most of the stuff we do day to day, we don't learn through reinforcement learning. We just learn through exploring the world as a child and learning models and being able to deploy those models in new situations. We don't often get told a task and then sit there and learn it through trial and error over and over again. So I think there's this misconception in the reinforcement learning community that reinforcement learning is the way that humans learn. Often that's writing is the motivation for reinforcement learning, but when you think about it, it's not really how humans learn until we get to the point where the task is too complex for us to use our previous models of the world, and we have to start doing trial and error. So we have to start swinging a racket to try and hit a ball, because that's not something we ever learned as a baby, or learning how to play a guitar, because that's something that's new and something that the average human just hasn't picked up on through their life. But yeah, I think this idea that humans learn everything through a reward function, which they then optimize for, isn't true, because babies don't know what they're supposed to be learning in the first place.
Yeah, that was actually the second question I had, because like kind of how does this, does evolution or individuals or biological creatures created from evolution actually have a reward? Because it seems as if it's more like a sort of like, the goal is to survive, obviously, because of if a individual survives, then they obviously just replicate and then carry on the species. But like, there doesn't seem to be an inherent sort of reward associated with their day-to-day kind of activities. Obviously, like if a lion or something catches some prey and they eat it, they get some reward in terms of like dopamine or like not feeling hungry or something. But there doesn't seem to be like a single reward just like governing all these actions. So I was wondering, like, is there kind of a analogous kind of thing with kind of machine learning or robotic learning that tries to kind of mimic that?
So I think, yeah, so maybe what you're getting at is, I guess if we go back to the question of how babies learn, babies certainly explore the world, but it's in quite an unsupervised way. So, you just leave a baby to its own accord, it will start trying to pick up objects and messing around with them, even though you haven't told the baby, oh, can you pick up this object and put it on top of that object? The baby will still do that. So there must be some reason the baby does that rather than just random movement. Okay, there's something which is the baby is thinking, it's interesting to try and explore what happens when I pick this object up. So I think there must be some kind of reward function there that is tailored towards encouraging exploration and encouraging skill learning. But it would be quite a high level reward function that, for example, will encourage a baby to try things that it doesn't know how to do yet, or try things that it's unsure of the consequences of. And that's something we certainly do in robot learning. There are a lot of sort of unsupervised robot learning algorithms which attempt to use predictive models of the future, for example, to encourage robots to explore states the robot is uncertain of. And that might then lead to a robot learning repertoire of skills, which it can then use later on downstream tasks to quickly learn those tasks rather than having to learn them from scratch.